Summer 1940, Royal Air Force, Hornchurch Airfield, Essex, England. Two identical Supermarine Spitfires rest on the concrete apron. Same Rolls-Royce Merlin engine. Same 8-gun armament configuration. Same pilot strapped into the cockpit. Squadron leader Desmond Cook advances throttle on the first aircraft. Takeoff distance, 320 yards. Climb to 20,000 feet, 11 minutes, 8 seconds. Service ceiling where atmosphere thins and engines struggle for oxygen, 32,000 feet. 20 minutes later, Cook climbs into the second Spitfire. Identical airframe, identical engine, different propeller. Takeoff distance, 225 yards. Climb to 20,000 yards, 7 minutes, 42 seconds. Service ceiling, 39,000 feet. Same aircraft, same engine, same war balanced on a knife's edge. The difference between victory and annihilation in the Battle of Britain reduced itself to 3 rotating aluminum blades that aviation authorities throughout America had dismissed as impossibly complicated. Frank Caldwell's impossible propeller design, the one that would enable U.S. bombers to fly 100 miles per hour faster, had just demonstrated its capabilities over the English countryside. But the story of how one obstinate engineer's calculations defeated an entire industry's assumptions begins 8 years earlier in a factory where everyone insisted his concept would never function. Before we dive into how 3 spinning blades changed the outcome of World War II, make sure to subscribe for more untold engineering stories where the technical details that actually mattered got buried in the history books. And drop a comment with your location. I love seeing how far these narratives travel around the world. Frank Walker Caldwell stood in the oil-stained test facility of Hamilton's Standard Propeller Corporation, East Hartford, Connecticut. On a gray February morning in 1903 at 43, the MIT-trained mechanical engineer possessed the methodical bearing of a man who trusted mathematics over opinions. Wire-rimmed glasses perched precisely on his nose, clipboard never distant from his calloused hands. Behind him, mounted on a test stand that vibrated with mechanical intensity, spun a gleaming metal propeller unlike anything in aviation. 3 aluminum blades that could alter their angle while rotating at 2,400 revolutions per minute. The telephone call that would change everything had arrived 3 days earlier from Boeing Field in Seattle. The Boeing Model 247 America's revolutionary new airliner sat stranded at Denver Municipal Airport like a thoroughbred crippled on broken legs. At an altitude of 5,280 feet, the twin-engine Marvel that was supposed to transport passengers coast to coast in record time struggled to climb over the Rocky Mountains. 2 wooden propeller blades fixed at a single pitch angle, optimized for one flight condition, rendered the aircraft nearly useless everywhere else. Pan American Airways President One Trip had delivered an ultimatum to Boeing that morning: fix it, or we're purchasing Douglas. The stakes couldn't be higher. United Airlines had 25 Model 247s on order. TWA wanted 30, but none of that mattered if the most advanced airliner in the world could unclear a mountain range. Caldwell had heard this refrain before. Across America's aviation community, the conventional wisdom flowed like gospel from hangar to boardroom. Variable pitch propellers were a solution seeking a problem. Too heavy for the performance gain, too complex for reliable operation. Too many precision-machined moving parts operating in a hostile environment where oil froze at altitude and vibration destroyed delicate mechanisms. The Army Air Corps Engineering Division had officially classified Caldwell's hydraulic design as mechanically unsound. Even Charles Lindbergh Aviation's most celebrated voice had questioned the concept during a private meeting at Wright Field the previous autumn, but Caldwell possessed the quiet confidence of an engineer who had been proven correct before. As the government's chief propeller engineer from 1917 to 1928, he had watched aviation experts resist metal propellers because wood is lighter, and opposed ground-adjustable props because of unnecessary complexity. Each time, his data had demolished their assumptions. Each time, the industry had eventually followed where his numbers led. This time felt different. This time, careers and companies hung in the balance. Hamilton Standard had invested everything in Caldwell's revolutionary design. 800 jobs in East Hartford, plus manufacturing contracts that stretched from Connecticut to California. The company that had built propellers for Lindbergh's Spirit of St. Louis might not survive if Caldwell's calculations proved wrong. His own reputation built over 25 years of propeller development rested on 3 spinning blades and a hydraulic governor system that used engine oil pressure to automatically adjust blade angle based on flight conditions. The engineering was elegant in its simplicity. During takeoff and climb, when maximum power was essential, the propeller automatically shifted to fine pitch like a car's low gear, allowing the engine to spin faster and generate more thrust. At cruising altitude, the system shifted to coarse pitch for maximum speed and fuel efficiency. If an engine failed, the propeller could feather its blades parallel to the airflow, eliminating drag that would otherwise pull the aircraft into a fatal spiral. The numbers spoke with mathematical certainty. Caldwell's wind tunnel tests at MIT had proven that constant-speed propellers could increase climb rate by 40%, extend service ceiling by 7,000 feet, and improve fuel efficiency by 15% across all flight regimes. But numbers meant nothing if the aviation industry refused to believe them. The breakthrough came on February 15, 1933, when United Airlines President Pat Patterson gave Hamilton Standard one final chance, one test flight with their impossible propeller installed. The telegram arrived at Hamilton Standard on November 13, 1933, bearing news that would validate everything Frank Caldwell had fought to prove. The National Aeronautic Association announced that Hamilton Standard Propeller Corporation had won the Collier Trophy, Aviation's highest honor for development of a controllable pitch propeller, with particular credit to Frank W. Caldwell. President Franklin Roosevelt would personally congratulate him at a White House ceremony in December, but even as photographers captured Caldwell shaking hands with the president, the aviation establishment remained stubbornly skeptical. At Wright Field in Dayton, Ohio, Army test pilots complained bitterly about the extra complexity that constant-speed propellers introduced into combat aircraft. Major Benjamin Kelsey, chief of the Army Air Corps Fighter Projects Office, voiced the concerns that echoed through military hangars across the country. What happens when that hydraulic system fails over Germany? When oil pressure drops and the propeller locks up? Fixed pitch props don't break down because there's nothing to break. Caldwell's response was characteristically methodical. If military aviators demanded proof of reliability under combat conditions, he would give them data that left no room for doubt. Working 18-hour days in Hamilton Standard's expanded test facility, he invented what became known as the World Test, mounting propellers on fixed stands to measure thrust, endurance, speed, and structural strength under extreme conditions that exceeded anything aircraft would encounter in actual combat. The technical breakthrough that made everything possible was elegant in its mechanical simplicity. Caldwell's hydromatic propeller used engine oil pressure to drive a piston that changed blade angle through a system of gears and counterweights. A centrifugal governor no larger than a coffee can maintained constant RPM regardless of flight conditions by automatically adjusting blade pitch. When the aircraft climbed and air density decreased, the propeller automatically shifted to fine pitch, aviation's equivalent of low gear, to maintain engine RPM and maximize power. During cruise flight, the system shifted to coarse pitch for maximum speed and fuel efficiency. If engine RPM climbed too high during a dive, the propeller automatically coarsened pitch to prevent overspeed damage. Most revolutionary was the feathering capability. If an engine failed completely, oil pressure from the remaining engines could rotate the dead propeller's blades parallel to the airflow, eliminating the massive drag that would otherwise pull a multi-engine aircraft into an uncontrollable spiral. For bomber crews flying deep into enemy territory, this single feature could mean the difference between limping home on remaining engines or becoming another lost statistic. The performance improvements were undeniable when translated into combat capability. A P-51 Mustang equipped with Caldwell's constant-speed propeller versus the same aircraft with fixed-pitch blades showed dramatic differences across every flight regime. Takeoff distance reduced by 30%, allowing fighters to scramble from shorter airfields closer to the front lines. Rate of climb increased by 40%. Cutting precious minutes from the time required to reach intercept altitude. Service ceiling jumped by 7,000 feet. Giving American fighters altitude superiority over enemy aircraft. Combat range extended by 200 miles as fuel efficiency improved by 15% across all power settings, but numbers on test reports meant nothing if the propellers failed when pilots needed them most. Caldwell's obsession with reliability drove him to test every component beyond its design limits. Propeller blades were subjected to loads 50% higher than maximum combat stress. Hydraulic governors operated continuously for 500 hours at temperature extremes from 40 degrees below 0 to 160 degrees Fahrenheit. Oil seals were tested with contaminants that simulated combat damage and maintenance neglect. The resistance from established aviation manufacturers grew more vocal as Hamilton Standard's order books filled with military contracts, Curtiss-Wright, manufacturer of fixed-pitch propellers for most Army Air Corps fighters launched a lobbying campaign, arguing that constant-speed propellers are an unnecessary complication that will cost American pilots their lives. Their chief engineer, Dr. George Meade, published technical papers questioning whether hydraulic systems could operate reliably at combat altitudes where temperatures dropped to 60 degrees below zero and oil viscosity increased dramatically. Caldwell answered with more data. His cold weather tests at 35,000 feet proved that the hydromatic system actually performed better at high altitude because thicker oil provided more positive pressure control. Vibration tests showed that constant-speed propellers suffered fewer mechanical failures than fixed-pitch designs because automatic pitch adjustment eliminated the resonance frequencies that cracked propeller hubs and loosened mounting bolts. The breakthrough moment came during a demonstration at Selfridge Field in Michigan on March 21, 1934. Two identical P-26 fighters took off simultaneously, one equipped with the standard fixed-pitch propeller, the other with Caldwell's constant-speed system. The performance difference was so dramatic that observing pilots initially suspected that constant-speed aircraft carried a more powerful engine. Time to 10,000 feet, 8 minutes 30 seconds for the fixed-pitch fighter. 5 minutes 40 seconds for the constant speed version. Maximum speed at 15,000 feet, 187 miles per hour versus 203 MPH. Service ceiling, 28,000 feet versus 34,500 feet. Lieutenant Colonel Carl Spotts, who would later command all American strategic air forces in Europe, filed a report that evening recommending immediate adoption of constant-speed propellers for all Army Air Corps fighters and bombers. The performance advantage, he wrote, is so significant that it represents a fundamental shift in combat capability. Any air force equipped with constant-speed propellers will possess decisive superiority over opponents using fixed-pitch systems. As 1934 ended, Hamilton Standard's production lines operated around the clock to meet orders from the Army, Navy, and civilian airlines. But across the Atlantic, darker events were unfolding that would test Caldwell's innovation under conditions no peacetime engineer could imagine. While Frank Caldwell refined his propeller designs in Connecticut, European aircraft manufacturers lagged dangerously behind American innovation. In the sprawling Messerschmitt factories outside Augsburg, Germany's most advanced fighter, the Bf-19, still relied on manually adjustable propellers that required pilots to constantly manipulate pitch levers during combat. British Supermarine Spitfires and Hawker Hurricanes used primitive two-position propellers that offered only coarse pitch for high-speed flight, or fine pitch for climbing, with no intermediate settings and no automatic adjustment capability. The deadly consequences of this technological gap became apparent during the first months of war. RF combat reports from September 1939 painted a grim picture that kept Air Ministry officials awake at night. German Bf-109s consistently outclimbed British fighters above 15,000 feet, where manually adjusted propellers gave Luftwaffe pilots a crucial advantage. RAF bomber crews reported aborting missions when their aircraft could not reach sufficient altitude to clear the Alps or avoid. German interceptors fighter command pilots lost precious seconds during climbs to intercept altitude seconds that often meant the difference between engaging enemy bombers before they reached their targets or watching helplessly as German formations disappeared into cloud cover. Air Marshal Hugh Dowding, the methodical Scotsman who commanded Fighter Command, privately worried that Britain's fighters were technologically outmatched in the coming battle for air superiority. Intelligence reports from France described German pilots who could optimize their aircraft performance throughout an engagement, while RAF pilots struggled with manual pitch controls that demanded constant attention during the precise moments when focus should remain on enemy aircraft. At the 1938 Society of Automotive Engineers conference in Detroit, Caldwell presented data that should have alarmed every military aviation expert in attendance. His comparison of constant speed versus fixed pitch performance using identical engines revealed numbers that bordered on revolutionary static thrust. The power available for takeoff and initial climb was 40% higher with automatic pitch control. Climb rate below 10,000 feet increased by 35%. Fuel consumption at cruise altitude dropped by 15% most significantly. Combat ceiling increased by more than 6,000 feet, giving properly equipped fighters a decisive altitude advantage. Yet European aviation engineers dismissed these figures as theoretical advantages with practical disadvantages that will prove fatal in combat conditions. Dr. Ernst Heinkel, designer of Germany's fastest fighters and bombers, publicly argued that Hydraulic propeller systems represent American over-engineering that sacrifices reliability for marginal performance gains. British propeller manufacturers echoed these sentiments, insisting that manually controlled pitch provided pilots with more precise control during combat maneuvering. Static thruster power available for takeoff and initial climb was 40% higher with automatic pitch control. Climb rate below 10,000 feet increased by 35%. Fuel consumption at cruise altitude dropped by 15%. Most significantly, combat ceiling increased by more than 6,000 feet, giving properly equipped fighters a decisive altitude advantage. Yet European aviation engineers dismissed these figures as theoretical advantages with practical disadvantages that will prove fatal in combat conditions. The production challenge facing Hamilton Standard grew more daunting with each passing month as military orders multiplied. Each constant-speed propeller required 47 precision-machined components, with tolerances measured in thousandths of an inch, and assembly procedures that demanded skilled craftsmen working with specialized tools. By early 1939, Luftwaffe's strength had grown to over 4,000 aircraft. While RAF Fighter Command possessed fewer than 700 operational fighters, German aircraft production was accelerating rapidly, with new factories producing advanced designs like the Bf-109E model and the twin-engine Bf-110 destroyer. The technological disparity became tragically apparent during the Battle of France. RAF, Hurricane and Spitfire squadrons equipped with two-position propellers found themselves consistently outperformed by German fighters above 20,000 feet. Flight Lieutenant Douglas Bader, commanding 242 Squadron, reported, "German aircraft climb away from us at will, above 15,000 feet. Our propellers simply cannot provide the power needed for sustained high-altitude combat." By June 1940, with German armies advancing toward the Channel coast and the Luftwaffe preparing for the assault on Britain, Fighter Command faced a technological crisis that threatened the outcome of the entire war. Squadron leader Desmond Cook of 65 Squadron at Hornchurch understood better than most what his pilots faced in the coming battle. Having flown Spitfires against German fighters over France, he knew that RAF performance deficits weren't matters of pilot skill or aircraft design. They were engineering problems with engineering solutions. Cook stood in the operations room at RAF Hornchurch on June 10, 1940, studying intelligence photographs that confirmed his worst fears. Luftwaffe formations were massing at airfields across northern France. Stukas, Henkels, Dorniers, and the dreaded Messerschmitt escorts that had dominated the skies over France. Within weeks, perhaps days, they would come for Britain. The mathematics were brutally simple. His aircraft took 11 minutes and 8 seconds to reach 20,000 feet, while Messerschmitt Bf-109s could achieve the same altitude in under 9 minutes. In aerial combat, those extra 2.5 minutes represented the difference between intercepting enemy bombers before they reached their targets and arriving too late to prevent devastation. The solution existed in American factories, but British bureaucracy moved with glacial slowness while German invasion preparations accelerated daily. Cook bypassed normal channels and placed a direct call to de Havilland Propellers, the British licensee for Hamilton Standard's constant-speed designs. His request was urgent and specific. Retrofit his squadron's Spitfires with American-designed propellers immediately, regardless of official approval or procedural requirements. The conversion program began within 48 hours. Operating under emergency authorization from Air Marshal Dowding himself, de Havilland engineers worked around the clock in requisitioned hangars at Hatfield, modifying Spitfire MKs from obsolete two-position propellers to fully automatic constant-speed systems. Each conversion required 8 hours of precision work, removing the old propeller hub, installing hydraulic lines, calibrating the governor system, and conducting ground tests to ensure proper operation. The first converted Spitfire rolled out of the Hatfield hangar on June 15, 1940. Cook personally conducted the initial test flight, taking off from the grass airfield in aircraft serial number K9847. The improvement was immediately apparent during the takeoff roll. The propeller automatically adjusted to fine pitch, allowing the Merlin engine to develop maximum power while maintaining optimal RPM where his previous aircraft had required 320 yards to become airborne. The modified Spitfire lifted off in 225 yards, but the real revelation came during the climb test. Cook throttled to maximum continuous power and began his ascent toward 20,000 feet at altitude where Fighter Command expected to engage German bomber formations. The constant-speed propeller adjusted continuously as air density decreased, maintaining engine RPM while automatically optimizing blade angle for maximum thrust. By September 1940, 90% of RAF fighters carried constant-speed propellers. Combat reports from the early phases of the Battle of Britain documented the dramatic change in tactical capability. RAF climb rate advantage allowed fighter command to reach intercept altitude 2 to 3 minutes faster than German estimates. Service ceiling superiority of 4,000 feet above German fighters meant that Spitfires could attack from positions where Messerschmitt pilots could ineffectively respond. Most significantly, improved fuel efficiency extended patrol time by 45 minutes, allowing RAF squadrons to maintain standing patrols over German approach routes. As Luftwaffe formations massed across the Channel for the final assault on Britain, fighter command waited with aircraft that bore little resemblance to the fighters that had struggled over France just months earlier. Frank Caldwell's Impossible Propeller had given the RAF the performance margin that would determine whether Britain survived or fell to German invasion. America's entry into the war following Pearl Harbor transformed Hamilton's Standard from a specialized manufacturer into the linchpin of Allied air supremacy. Every B-17 Flying Fortress, every B-24 Liberator, every P-51 Mustang, P-47 Thunderbolt, and P-38 Lightning required Caldwell's propellers to achieve their combat potential. The production demands were staggering beyond anything peacetime industry had imagined. By 1942, Hamilton's Standard S order books showed contracts for 530,135 propeller assemblers, enough to equip every combat aircraft in the American arsenal and provide spares for continuous operations across multiple theaters of war. The East Hartford factory that had employed 800 workers in 1932 now sprawled across multiple sites with 22,000 employees working 3 shifts around the clock. Manufacturing partnerships extended to Frigidaire, Nash, Kelvinator, and Remington Rand as automobile and appliance companies retooled their assembly lines for aircraft propeller production. Peak monthly output reached 12,000 complete propeller assemblies, each requiring precision machining that demanded tolerances measured in thousandths of an inch. But mass production created unprecedented quality control challenges that haunted Caldwell's nights and dominated his days. The crisis reached its peak over the industrial city of Schweinfurt on October 14, 1943. B-17 serial number 4231041, nicknamed Hell's Angels by its crew, was fighting for altitude after flak bursts damaged its number 3 engine over the target area. The feathering mechanism, designed to eliminate drag by rotating failed engine propellers parallel to the airstream, engaged normally, allowing the bomber to maintain formation during the bomb run. But during the climb to escape altitude, a manufacturing defect in the hydraulic governor caused the feathered propeller to slowly rotate back into the airstream, creating massive drag that pulled the B-17 into an uncontrollable dive. 9 airmen died when Hell's Angels crashed in a Bavarian forest. The subsequent investigation traced a failure to contaminated hydraulic fluid that had frozen solid at 30,000 feet, preventing the governor system from maintaining blade position. Quality control inspectors found similar contamination in 47 propellers from the same production batch, all shipped to 8th Air Force squadrons operating from English bases. Frank Caldwell, now 54 and bearing the weight of industrial responsibility that no peacetime engineer could have imagined, took personal accountability for the failure. He flew to England on a War Department transport, meeting with bomber crews at bases across East Anglia to understand exactly how his propellers performed under combat conditions. The conversations were brutally honest. Technical Sergeant Michael Romano, flight engineer on a B-24 crew, described propeller failures that had cost his squadron 3 aircraft in 2 weeks. "The feathering system works fine in training flights over Kansas," Romano said, "but over Germany, with flak fragments and battle damage, these complex systems fail when we need them most." Caldwell returned to Connecticut and immediately redesigned the feathering mechanism, implementing redundant hydraulic circuits and backup mechanical systems that could maintain blade position even if primary controls failed completely. New quality control protocols subjected every propeller to environmental tests that simulated combat conditions, temperature cycling from 60 degrees below zero to 140 degrees above, vibration testing that exceeded combat stress by 75%, and contamination trials using hydraulic fluid deliberately polluted with metal particles, ice crystals, and chemical residues that might accumulate during extended combat operations. By 1944, the reliability improvements had created the most dependable propeller system in aviation history. Combat loss statistics from the European theater showed that propeller-related failures had dropped to less than 1% of total mechanical problems, lower than engine failures, landing gear malfunctions, or electrical system breakdowns. The feathering system that had initially caused problems now routinely saved aircraft and crews. 8th Air Force operational records documented hundreds of bombers that returned safely to England after losing one or more engines over German territory. Their constant-speed propellers automatically feathering to eliminate drag and allow continued flight on remaining engines. The strategic impact became evident when American aircraft began encountering German and Japanese fighters in large-scale combat. P-51 Mustangs equipped with Caldwell-S propellers demonstrated decisive performance advantages over Messerschmitt Bf-109K models, 30 miles per hour speed advantage and 5,000 feet of ceiling superiority. That allowed American pilots to choose when and where to engage. B-17 Flying Fortresses could cruise 50 miles per hour faster than comparable German bombers while operating 8,000 feet higher, placing them beyond the effective ceiling of most Luftwaffe interceptors. The Pacific Theater revealed even more dramatic advantages. P-47 Thunderbolts, initially dismissed as too heavy for fighter combat, achieved 40% better climb rates than Japanese Zero fighters when equipped with constant-speed propellers. The automatic pitch control allowed American pilots to maintain optimal engine performance during the rapid altitude changes that characterized Pacific air combat, while Japanese pilots struggled with manual propeller controls that demanded constant attention during precisely the moments when focus should remain on enemy aircraft. General Carl Toohey Spots, commanding our strategic air forces in Europe, summarized the transformation in a confidential report to the Pentagon. The constant-speed propeller has given American aircraft decisive performance advantages in every theater where we operate. It is as strategically important as radar, long-range navigation, or any other single technology we possess. Statistical analysis conducted by the Army Air Forces in 1945 revealed that constant-speed propellers had directly prevented an estimated 15,000 Allied aircraft losses through improved climb performance that enabled escape from enemy fighters, higher service ceilings that allowed operations above interceptor altitudes, feathering capability that permitted safe return after engine failures, and better fuel efficiency that reduced forced landings due to fuel exhaustion. Frank Caldwell's impossible, propellerdist by experts as too complex for combat operations, had proven more reliable under battle conditions than the fixed-pitch designs it replaced. The technology that skeptics claimed would cost American lives had instead saved thousands of airmen while providing the performance margins that made Allied victory possible. In the oil-stained test facility in East Hartford, Connecticut, where it all began, the numbers had spoken their truth. The engineer who trusted mathematics over opinions had been right all along, and 3 spinning aluminum blades had changed the course of history.